We share low Earth orbit with a massive, high-speed cloud of orbital shrapnel. Right now, there are over 27,000 cataloged objects and an estimated 1 million smaller fragments, larger than a centimeter, zipping around the planet. Navigating this minefield requires constant physical adjustment. The SpaceX Starlink constellation alone executes approximately 1,700 avoidance maneuvers every single month to dodge these fragments. Those maneuvers depend entirely on ground-based tracking. A telescope captures a brief streak of light against the background stars. From that fleeting observation, operators generate a two-line element, or TLE, a mathematical model of the object's trajectory. Every collision avoidance decision is based on these TLEs. The limiting factor is time. Ground-based optical telescopes typically only observe a piece of debris for 5 to 10 minutes per pass, before it slips back into the Earth's shadow or beyond the horizon. The entire collision safety architecture of low Earth orbit rests entirely on the mathematical fidelity we can extract from those first few minutes of optical tracking data. To compute those initial orbits, the space industry often defaults to mathematical methods developed in the 19th century. Classical Gauss initial orbit determination requires only 3 observations to establish an orbit. Gauss relies on a sector triangle approximation. It assumes the area swept by the orbit over time behaves linearly. But for very short arcs in low Earth orbit, higher-order physical corrections diverge rapidly, making this approximation physically ill-suited for the environment. This chart displays the inclination error of various tracking methods. Looking at the red bar on the left, Gauss IOD produces massive inclination errors of 5 to 15 degrees over a standard 8-minute optical pass. If you propagate a 10-degree inclination error forward by 24 hours, the debris fragment ends up hundreds of kilometers away from its predicted location. This positional uncertainty triggers a phenomenon known as the false alarm maneuver. Satellite operators execute avoidance burns not because they know a collision is imminent, but because the mathematical uncertainty of the debris path is too large to ignore. Operators often use the SGP4 algorithm to project these orbits forward. SGP4 is a highly capable propagator, but it is bound by its inputs. If the initial TLE it receives is off by 5 degrees, it faithfully propagates that exact 5-degree error into the future. Because their initial orbit determination tools lack structural precision, constellation operators are trapped in a costly cycle of precautionary maneuvers. To fix this precision gap, we have to account for the actual shape of the Earth. Earth is not a perfect sphere, it bulges at the equator. This physical oblateness creates a gravitational effect called the J2 perturbation. In low Earth orbit, specifically around 400 kilometers in altitude, that equatorial bulge pulls continuously on passing objects, causing their orbits to rapidly precess. This graph charts J2 position drift over time. Notice the intersection at 8 minutes. J2 perturbation causes 1.27 kilometers of positional drift. The adjacent bar chart shows that 1.27 kilometers is 74 times larger than the telescope's baseline noise floor. Standard Keplerian models assume a perfectly spherical Earth. Because the J2 drift heavily outweighs the instrument noise, any mathematical model that ignores J2 is biased from the very first second of calculation. The framework introduces equations 1 through 3, calculating the specific J2 acceleration components in Earth-centered inertial coordinates to map this exact physical divergence. A method called Polygon Closure IOD takes these equations and uses a J2-corrected Runge-Kutta numerical propagator to accurately solve the orbital boundary value problem. By integrating this numerical propagator, the J2-corrected arcs achieve tightly bound position residuals of less than 1/10,000th of a kilometer. Aligning orbit determination with the sub-arc-second precision of modern tracking sensors requires this strict physical rigor. J2 correction is a mandatory requirement. Classical methods attempt to derive an orbit from a single epoch, a single reference point in time. Polygon closure abandons that approach for a multi-anchor structure spanning the full observation window. This polar diagram illustrates the geometry of an 8-minute pass. Polygon closure extracts 4 distinct anchor observations, marked by the red diamonds, distributed internally across the sequence. The algorithm mathematically links these 4 points together using 3 discrete J2-corrected orbital arcs. At each of the inner anchor points, it enforces a velocity closure constraint. The exact velocity of the debris arriving on one arc must perfectly match its departure velocity on the subsequent arc. This arrangement provides a massive computational advantage. Enforcing velocity continuity across these boundaries generates 6 mathematical constraints to solve for only 4 unknown range variables. This creates an overdetermined system, expressed as a matrix in equation 5. Here, the velocity discontinuities are driven exactly to 0, definitively locking the physical range parameters into place. Because there are more constraints than variables, the system narrows in on a unique, stable solution, even when the underlying optical observations contain astrometric noise. By anchoring the mathematics across the full spatial geometry of the pass, rather than a single point in time, Polygon Closure achieves a baseline stability that classical tools lack. To test this stability, researchers ran a controlled experiment using a circular debris orbit with an inclination of 32.4 degrees, passing directly over a tracking station situated at 32.4 degrees north latitude. As the debris passes directly through the zenith, the station's latitude temporarily matches the orbit's inclination. At that precise moment, the relative range rate drops to near zero, creating a mathematical blind spot known as geometric degeneracy. Systematic ranging, the current industry standard for optical-only orbit determination, relies entirely on measuring range and range rate at a single reference point. In this specific scenario, it breaks down. This chart compares the calculated orbit shapes. The red path shows the systematic ranging result. It calculated a highly elliptical, spurious orbit with an eccentricity of 0.50, entirely missing the true circular path. Returning to the inclination error chart, Polygon Closure IOD bypassed this zenith degeneracy entirely. By using 4 anchors across the full pass, it recovered the correct circular orbit with an inclination error of less than 0.005 of a degree. Systematic ranging produced a massive angular residual of over 75,000 arcseconds, completely rejected by standard thresholds. Moving to the semi-major axis error, it was off by 34%. Polygon Closure recovered the exact axis with just 0.001% error. When observation geometry collapses at the zenith, single epoch methods fail. An overdetermined polygon is mathematically required to maintain tracking continuity. Precision requires computational power. To isolate the correct range, the algorithm calculates hundreds of thousands of J2 correctable Lambert problems in seconds. To verify real-world viability, the software was optimized for ARM Cortex-X3 hardware, the precise processor architecture currently executing commands inside modern LEO satellite buses. This execution time chart reveals the performance benchmark. A highly parallelized C++ implementation processed the entire orbit determination protocol in just 227 milliseconds. This speed enables a strict operational pipeline. Telescopes collect the data, systematic ranging provides a fast initial screening of the admissible region, and Polygon Closure executes the high-precision TLE refinement before a final maneuver decision is made. That high-precision TLE translates directly into conserved physical resources. Every time a Starlink satellite fires its thrusters for an avoidance maneuver, it expends about 35 grams of highly valuable krypton propellant. By eliminating the massive inclination errors of classical methods, operators can drastically reduce false alarms. A 50% reduction in unnecessary maneuvers saves an estimated $2.2 million per year in launch and propellant costs for a Starlink-scale constellation. Upgrading from a 19th century approximation to a J2 corrected, overdetermined framework yields highly accurate orbits in fractions of a second. Polygon Closure is a hardware-optimized economic asset designed to keep low Earth orbit operational and sustainable.